So now the way it is done is to recognize, you can go over that, you recognize that you can decompose the partition function just like we did. You can decompose the partition function in terms of a matrices, and these matrices are very simple matrix. These are the matrices that it comes. So these are the diagonal terms, and you can essentially use this matrix to propagate the nearest neighbor correlations to all order, and you do very similar thing that we have done here to the power n. And then, but you cannot decompose completely like that I have done here, because of the B introduce an asymmetry in the problem. The symmetry that I have in this problem, that is broken because of this term, because here now here 2 down comes with the same term, with 2 up, but here that is reflected here, 2 up and 2 down are not the same, because see, B is the magnetic field. So when you are going down, then magnetic field, if the spin is up, then both the 2 spins down will be unfavorable. So that will come as a plus sign. Otherwise, both spins up, that will come with a negative sign. So this symmetry of this Ising Hamiltonian in the absence of the magnetic field is broken as it should in this case, in the presence of the magnetic field, by this term. Then one can solve this. Let me tell you, by transfer matrix method with the diagonalization. The reason of my not doing it, it uses some theorems of eigenvalue analysis, which will take a long time to do. That I am not going to do, but I'll tell you and there is some examples done. You will see that particularly what happened when you have these kind of spins, which are kind of things that I have a little better than how one configurations gets energy, and how you can calculate the eigenvalues of such things. But let me tell you the result. Okay, and the result is interesting, but not almost the same kind of thing that we have. So this is the partition function now. That's what I was saying. It includes the calculation of the eigenvalues, which you find most of the books assume the eigenvalues of this matrix. This matrix, you have to find the eigenvalues of that matrix, and then you notice that one eigenvalue is larger than the other eigenvalue, and then you can like here, these 2 eigenvalues analysis done here, and one is larger than the other one. So in the end, going to infinity, one of them remains. But let me tell you the basic result. The final result is this: the partition function IQI for Ising in the presence of the magnetic field is a considerably more complicated, but still analytically doable. You can go through these. These have to be done analysis. Then you have to do certain. It's not too difficult. Very similar thing that we did in the absence of the magnetic field. Same factorization, and then the sum over all these things. This is the theorem I was saying. I am not comfortable about doing that. That quantity is the trace of m to the power n. And then of course you have to have certain kind of unitary. This is a symmetric matrix. Then unitary transformation of the symmetric matrix, and then partition function come as this diagonal matrix, diagonal to the power n, and then that is this to the power n. This is then the diagonal matrix to the power n is exactly equal to that. So I don't want to go through all this, but These are mathematics you can do, and they are not difficult mathematics, but you have to do them. All right. So this is the this is all given there. So the partition function then becomes this thing at one. Look at that, how much more complication we have when the electric field, magnetic field is there, and then you go to, if I would be equal to 0, then it will go over to the old form. Then we can calculate the free energy, cavity L and Q Ising, using that Ising, and then you can get the, as I said, one of the eigenvalues. One of the eigenvalues survive because other ones is more. So n going to infinity limit, this is negligible with respect to that one. These are the asymptotic analysis. And then you get this free energy. And this is very interesting. Once you have free energy, then we can do some work with that. We couldn't do something over there in the earlier one that I have worked out here because we didn't have magnetic field. I could have do entropy and I could have done specific heat, but I couldn't do the most important thing that people want, which is the magnetization. But if I have the free energy, I can do the magnetization. Now, can you tell me how to get the magnetization from this free energy? I know I'm dumping some equations on you, but they're not really very difficult. Beyond what I've done here was the tricky little thing. After that, it is same. Though you have to do the unitary matrix transformation, you have to do the eigenvalue analysis, all these things. It will take more than 40 minutes to do. So I'm just avoiding doing it. How do I get, when I have the free energy, how do I get the magnetization? Lighter, right? Yeah. So all I have to do dIdB, and I get the magnetization. Okay, that is done here. Then magnetization is with respect to magnetic field, and H is same as B, magnetic moment taken out. Okay. So this is then this quantity. Then one can calculate, going back to same as this lambda plus and all these things, and okay, and then you get, call that or combine this as Y, and then we have taken with respect to magnetic field, and that's why you have to take care of the magnetic moment. Will come here and there, change of variable, I have to absorb it here because this is the quantity that I need as my magnetization. I want to go back to the variable I have in my work, which is this Y, and Y is this quantity, beta B, and then I can take the derivative. These are the ugly things that one doesn't want to do in the class, but you can do it. Fortunately, it is done here. So I can do the derivative of this ln. So this guy comes in the denominator, and you take the derivative, you get two terms. Okay. Taking derivative of cos and all these things is certainly not the most pleasant thing in the world. So because there are two terms there, but you can do it. But essentially, I think everything is clear here, right? Nothing should be complicated. Doing the board is complicated, especially sign. I'm mortally afraid of science. Okay. Now we get this beautiful expression. However, at the end of the day, you can simplify that. That remains, this remains, and there is this gets simplified, and I think we have to define variables as x, not x, maybe p and q, small p and small q, and again do that, and this should become the same as this. I think we have to think of, we have to go back to e to the power x and e to the power minus x, or e to the power y and e to the power minus y, and square all these things. Then we have to combine term. I think here also you have to combine term. This and this is the same. and that is different from this one. But whatever. This and this is the same. So I think there is certain manipulation one needs to do that. I have not done that for a very long time, but you can do that. But at the end of the day, you get the magnetic moment, which is experimental observable quite easily in these magnetic systems. You get a completely analytical form. That is the main thing. That is a sinh, and sinh is as analytic as cosh, hyperbolic cosh. So, and now I plot that against 1 over temperature. Now, if there are a phase transition, what would I expect? I am plotting is 1 over temperature. So, this is a high temperature limit and this is a low temperature limit, right? If there is a magnetic transition, paramagnetic to ferromagnetic transition, then what will happen? Now tell me, what is the ferromagnetic state? Tell me, what is the ferromagnetic state? See, one of the reasons that physics course, they learn it very quickly, very rigorously in your first year. You learned it, but not in terms of spins in your schools. They should have taught you in terms of spins. They need not solve the Ising model, but they should have told you about the Ising model. But that's not done, not in Indian context. But Ising is a very beautiful thing. And the little thing I did, the little thing that I did here could have been done in high school also. But doesn't matter what the solution. Forget about that, what has not been done, not done. Now tell me, what is the ferromagnetic state? See, we are doing phase transition, and now the most important phase transition is the magnetic transition. Then metal insulator transition, which is huge amount of industry runs on that, right? Then semiconductor, superconductivity. Did anybody teach you magnetism? Huh? Magnetism has not been taught at all. But in the integrated PhD, it has not been taught yet. They should have taught one magnetism course. Electrostatics, electromagnetism, because we had that a little bit in our honors course. We had it one small 16, half of a course in Calcutta University, magnetism, and then I took a lot of courses there from physics department. But I tell you that it's really rewarding. Those of you going to material science and physical chemistry, I hope some of you are going there, because that's the most fascinating area now. And let me tell you, organic chemistry is not that fascinating anymore. It's going on and on and on, the same kind of synthesis. Well, you can get some job, but it's very boring. So most exciting things are happening at the world of material science and world of biology. Materials is particularly exciting now, as you can see. Your TV getting changed, your mobile getting changed, every technology is getting changed in every 2-3 years. Huge amount of work going on in all these companies, IBM, Samsung. We should do more of this. Now the artificial intelligence is going integrated with okay. Ferromagnetic is that when all these spins are parallel to each other. That's the ferromagnetic state. And paramagnetic state is that when the spins are random. So ferromagnetic state is the state we call ordered state. And paramagnetic is the disordered state. So what we are talking of, an ordered disorder transition. It's a very important thing. Please write it down. Ordered disorder transition is an example of ordered disorder transition, which is same in melting, which is same when you have a beta brass, which I believe is zinc and copper, right? And that undergoes a fabulous transition, which is a huge change of material properties. So, and we use that material properties. Many times you see when you use the valve, safety valve, that we put an alloy, and a little change of temperature change the properties of the alloy. That is the basic of this, many of the valve in these complex systems. So these are important thing to know, because chemists make these things, and then we just give it to for physicists to do everything, characterization. If we understand, we could have make much better material probably. Okay, so the ordered disorder transition. Then what would happen in a real system? You'd see that there would be a hysteresis. There would be sudden jump of magnetization, this is 1 over temperature, so it will be other way around. If I put temperature, it will be like that, otherwise it will be like that, go like that. So that's a and this system show the hysteresis, and as I told you, a system that shows hysteresis is the first order phase transitions. However, the beauty you see in a two-dimensional system, that even in the absence of the magnetic field, there is a order disorder transition where the specific heat compress magnetic susceptibility, so that diverges, and that's the characteristics of an order disorder or a critical phenomena. So the one of the things that Ising model can use us, and that I am going to use to take you to a critical phenomena. Okay, so before we go, so this is the, as far one-dimensional Ising model goes, I have derived a part of it, the basic thing, and I have, it is given here, we'll put it in the A. If we want to make a little changes, I'll probably make a little changes on this chapter and send it to you. But you can see there is a unitary transformation going over to diagonal, then to the power n is lambda 1 lambda n, and here you have to work it out, find out the eigenvalues, and here the same thing I have done, exactly same thing does here, that you go to a factorization. The same factorization comes here. That allows me to write it into n. Same thing m to the power n I wrote here. Okay, but then you have to go by eigenvalue analysis. I could sum it up here because I did have this symmetry which is not here. Okay, so now this is a hugely important thing, an extremely difficult thing at the same time, the two-dimensional Ising model. I will just tell you the result now, and I'll do something else which I want to teach you something else, which is the other part of Ising model, many other techniques which are very useful. So but let me continue a little bit with two-dimensional Ising model. I'll come back to the two-dimensional Ising model. In a normal course of event, I would not have two-dimensional Ising model at this stage. I will have a little later, and that's the way I teach. So two-dimensional Ising model, when I have a square lattice and I put these pins, the beauty of this is that this model exhibits a phase transition, and this played a very important role. As I told you, in the whole history of almost history of science, that can be solved exactly, and that is it was done by the evolution of the partition function is extremely highly non-trivial. The feat was achieved by Unsagat, still considered the most brutal and difficult calculation done in the entire physics, and that has a very complicated free and functional, which we are not going to. But most important thing, that has this magnetization transition. This is the model shows, and this is what you see in experiment. And it has, this fall has certain exponent, which is called critical exponent, and that is the things, critical phenomena, that we do a little later, study of the critical. Now I want to do not the solution, this is a highly non-trivial solution, but I want to do, this is what I want to do now, and I want to start is, there are certain ways, okay. There is a very important thing in magnetization, which is the Curie point. Now, can you tell me what is the Curie point? I really strongly recommend that you guys, I'll send you some material, but you read up the magnetism. It is really not fair not to know about magnetism. That is not fair. Even if you are doing, I at least indicate PhD students are after all doing PhD, right? And you would need, even if you are doing organic chemistry, the magnetic properties you have to study. And many of the things, the magnetic properties of organic materials, organic, that you know why magnetic is so important, magnetic properties are studied. The reason is that sometimes you have a lone pair or some characterization you need. So you need to know the basics of magnetism. Okay. So these are the uh, we'll make a beginning. So the way I'll go now, let me write down and I'll come back and forth. Few things you should certainly do. Go through the derivation. This will take you time, about an hour. Or maybe a little bit more, but this is worth doing. So the flow that I'm going to do is, we have done one-dimensional Ising model. We will not do, and we done the banditization and everything, and show there is no phase transition. No phase transition. There was a little bit hint of that, why it's the phase transition, that will come back later. Essentially because the new phase cannot be stabilized with only two nearest neighbor. And next what we will do is they called mean field theories. There's a huge list here. In this context of lattice is Bragg-Williams. Then the same as van der Waals, a much simpler and more elegant way is Landau. Landau theory, we did not do Landau theory yet, right? So we'll do the Landau theory after we finish these things. So in the mean field theories, you have done one example of mean field theory, that's what I was asking. Curie temperature of the molecular field. What is the Curie temperature? Also called Curie-Weiss theory or equation. What is that? Magnetization equal to 1 minus T by Tc. Remember that? The magnetization goes to 0. But magnetization goes to 0 with the exponent 1. If I go T minus Tc, then T minus T minus 1. And that is not correct. People found that we saw the 2D Ising is a very different experiment. Okay. So the Curie theory, the way it was developed, we will see that, was a mean field theory. Mean field theory is the following concept, that we have is a very important concept, but fortunately they are understandable in a very simple physical way, and that's what we'll do. And you will like the Bragg-Williams. I'm not bragging, but I once had the good fortune to teach at Harvard a really formal course, a course like that, StatMac. And there's a great hall called Pfizer Hall, where many great people have presented their results, and next to it was great Bob Woodward's laboratory. When you are that legend, Lipscomb and all the legends are there. But when you teach at that hall, the beauty of that is that when I go to teach, I used to teach from 11 to 12, 3 times a week. Everything is pakka. That means there are nine one screen, and screen can be taken out, and 9 boards. 9 board in the following sense: 3 row and 3 row, 3 column, and you press. You start from one side, do this, do that, then 3 goes up. You press and then 1. But more important, that's not. But what I'm saying, when you enter, the secretary, I told them, secretaries, in the morning I want my coffee for me and my students when they are rich. So there is coffee there, and everything was clean. All the chalks were ready. That's what the secretaries are supposed to do. Here, God knows what the secretaries do. Most of the time, they don't do anything, and we are not assigned job to them. So coming back, so this now I've got something nice. I complain a lot, but that's things improve by complaining only. Okay, so the mean field theory means I have, so let's say nearest neighbor. So I have spins here, spins here, spins here, spins here, and these are first nearest neighbor, right? And second nearest neighbor are these four. Okay. Now everywhere there is a spin and spins. So what is the main effect of the other spins on my central spin? Think a little, because this will be continue with the next class. So let us consider a very high dimensional solid, higher than 3 dimension. You can stop at 3, but in your mind you can consider. Then number of nearest neighbor increasing. Okay, here I have 4. 3D in simple cubic will be 6, like that. Now, I can have a magnetic field or not have a magnetic field. These spins are, what are they doing on this? They are interacting. How they are interacting? They are interacting their moments. Now for a moment, if I say I freeze this one, then I'll add the effects of all these things. What my spin will see then? My spin will see an average effect. So that is average and mean is the same, right? So then I'll have my spin here is seeing a mean field. So if all of them are up, then my spin here will also want to be half. So now can I take a description, little bit coarse grain, means opaque description, little bit, make it little, not completely microscopic, little bit less micro, we call it coarse graining, where I would be able to talk of I write the Hamiltonian now in terms of the mean field. Now what I do, these guys also acting on that guy, I can construct another mean field and I can make them self-consistent. Okay, that is one probably layer upper theory. So this is the way one can get beautiful solutions. They show the phase transitions. We don't have to do as much work, and I told you anyway, 3-dimensional Ising model, we cannot solve anything. Nobody in the world has been able to solve. But you will see this is just like Van der Waals equation. So we'll do these beautiful mean field theories. They are the very favorite of people because this is much easier to do the calculations and much easier to apply. Otherwise you have to do numerically in 3 dimension. And these mean field theories, as I said, very favorite of us, and we will continue with that in the next class.